Hi, and thank you so much for the invitation to speak to you all today. My name is Sylvia Dee, and I'm a climate scientist at Rice University. And thanks again so much to Tom for organizing this very important event. I've been asked to give you a presentation today about the science of climate change. So I'll just start off by giving you my take-home message, which is that climate change is simple in its science. The impacts are very serious, but the problem is solvable, which is the topic of today's consortium. So if you remember nothing else from my talk, I want you to bring home to your families, to your colleagues, to your scientific community that when we talk about climate change, it's imperative that we impart the message that this is not controversial science. It's been known for hundreds of years. We already see the severe impacts, which I'll talk about quite a bit today. And I'm delighted that my other co-speakers today will be talking about some of the solutions to the problem. A little bit of background about our very unique planet. Earth is in this very key zone in our solar system, which we call the habitable window in Earth science. We're far enough from the sun for water to condense, and we're also close enough to the sun that water doesn't freeze all the time like it does on Mars. And so Earth is really in the Goldilocks zone to support life. So when we talk about climate change, our motivation is really the habitability of our planet. And I always like to tell my students that the planet will survive. What we're concerned about is biodiversity and species such as our own surviving on our uniquely habitable planet. And importantly, we don't have an experimental Earth. Unlike our colleagues in physics and chemistry and biology, we cannot put the Earth in a test tube. And essentially now we're doing an active experiment on the planet, and we are seeing the outcomes of that experiment unfold before our eyes. But unfortunately, we do not have a planet B to go inhabit as a species. And so we're highly motivated to both understand the impacts of climate change and come to solutions to stop the problem from happening. Our atmosphere has been in delicate balance for millions of years. And importantly, during those millions of years, our species has evolved. And when we think about climate change, the basic energy balance of the planet, going back to the conservation of energy, is such that the energy we receive from the sun, so the energy in, must balance the energy that Earth returns to space. So we receive shortwave or visible radiation from the sun, and we emit longwave or infrared radiation back to space. In thermal equilibrium, these two quantities must be equal, and anytime there's an imbalance, we have climate change occur. And as it turns out, the composition of Earth's atmosphere is actually crucial for maintaining the temperature of our planet. So as that solar radiation enters our atmosphere, some of it is absorbed, and as it's absorbed at the surface, as some of it escapes to space, it's reabsorbed by what we call our greenhouse gases in the atmosphere. So these include carbon dioxide, methane, water vapor, and several others, which I'll get into. And because these gases absorb that outgoing long-wave radiation, they sort of act as an extra blanket over the planet. And without our greenhouse gases, our average temperature on the planet would be a frigid minus 16 to minus 19 degrees Celsius. And for reference, Mars is about minus 63 degrees Celsius. So again, it would be difficult to support life at these temperatures. So what's happening now? How are we altering the composition of our atmosphere? Essentially, we are adding more greenhouse gases to the atmosphere. We're adding more CO2, methane, etc. And so as this long-wave radiation attempts to escape to space, it's being trapped by a thicker blanket. With more CO2 in the atmosphere, it's more difficult for infrared radiation to escape to space. How does this work? I know I'm amongst a chemistry crowd, so just to be very specific about how greenhouse gases trap outgoing long-wave radiation, CO2 absorbs radiation in the radiation wavelength range that corresponds to this outgoing long-wave radiation. So CO2 is actually molecularly excited by radiation in the infrared domain. And in chemistry, we know that a molecule can be excited by light. So there are energy transitions and changes to different energy levels that occur in the electrons of these molecules. They can bend, they can stretch, they can asymmetrically stretch, and as they are excited, they deposit heat locally in the atmosphere. So thus radiation is converted into heat. And this is the background chemistry, atmospheric chemistry behind the greenhouse effect. In a natural greenhouse effect, we have solar radiation penetrate the atmosphere, heat up the surface, re-radiated heat escapes to space, and some of it is trapped in the atmosphere by our greenhouse gases. We are enhancing that greenhouse effect now, so we're essentially adding more of these heat-trapping gases to the atmosphere. It's very simple. You can think of it like we have a taller goalie playing soccer, or a more broad sponge sitting in the atmosphere sucking up heat as it's trying to escape to space. So the science is very simple. I'm already done with this part of the lecture. CO2 absorbs outgoing infrared radiation from Earth's surface, and if we increase CO2 concentrations in the atmosphere, we increase the amount of heat that the atmosphere can trap. And guess what? That's all there is to it. So you can think of, if you're trying to explain the greenhouse effect to a child, for example, imagine somebody came and put an extra blanket on you in the middle of the night. You would overheat, and that's exactly what the Earth is doing now. We're adding too many blankets to the atmosphere, and the Earth is overheating. So now we have a prediction based on atmospheric chemistry. And what questions can we start to ask about how this manifests in the climate system? So the key question I'll pose to you is, how do we know what's happening to the atmosphere and the oceans? To answer this question, we use three main tools. Number one is direct measurements of our weather and climate, so from weather stations or from satellites. We also use paleoclimate data, so data extending hundreds or thousands or millions of years into Earth's past, from tree rings and corals and ice cores, which extend the instrumental record back in time. And finally, we use climate models, which I'll talk about a bit later and is the topic of my research group at Rice. Our first tool, which I'll fondly call fancy weather instruments. You've all used a thermometer before and potentially a barometer, right? We have lots of different scientific instruments that we use to record the weather. This figure in the top left shows the distribution of present weather stations on Earth. We also have satellites. These are NASA's satellites that orbit the planet, taking measurements of things like temperature, sea level, CO2, carbon monoxide, every day orbiting Earth. And we also have information from ocean ship tracks, and we have ocean stations that are collecting this data in real time. Our satellite data only extends back to about the 1970s, but these measurements have been invaluable because they give complete global coverage. So what do these direct measurements tell us about how the Earth is changing? Our weather instruments show, when we aggregate them over the entire land surface, that the climate is warming. There's no surprise here. This is the global average temperature anomaly on the y-axis, and year from 1850 through the mid-2000s on the x-axis. And you can see that the temperature anomalies have categorically risen, and these are taken from three independent meteorological station data. So the Met Office, which is the UK Climate Research Center, NOAA, our own National Oceanic and Atmospheric Administration, and NASA's temperature. And importantly, you can also see that all three of these lines agree very well. So we have confidence that they're telling us something consistent. Satellites also show, since the 1970s, a modest temperature increase through 2010. This is an outdated measurement, but there's obviously a lot of natural variability in the climate system that's modulating this, but we can see that the trend is linearly up. We can actually visualize these changes in temperatures in a movie. So this short video shows temperature anomalies since the late 1800s. So this is the temperature difference from a base period. So the colder temperatures show it was colder than normal, and the warmer temperatures show it was warmer than normal. And after 1950, you can really see that we have a lot more red and orange colors. And towards the end of this video, you'll notice that there's quite extreme warming, especially at the poles, which is a phenomenon we call Arctic amplification. Plotting that video that I just showed you as a time series, These are global temperatures every year from 1850 to 2017. And without looking very closely at this, we can just see, each decade here, the planet has been warming substantially, with the 2010s and most recently, the last 5 years or so being the warmest year on record, beating the record from the previous year every single year. The amount of warming we observe at the poles is much more dramatic. It's on the order of 4 to 5 degrees compared to the global average of about 1 degree. And that has significant impacts on fields such as Arctic sea ice. We know that Arctic sea ice is potentially going to disappear within the next 10 years during the summertime. This is a graph showing the million square kilometers of Arctic sea ice from 1978 through 2010 as measured by satellites, and we can see that there's a clear downward trend. This is a visualization showing you the sea ice thickness in the Arctic Sea over time, which my colleague Zach Labe put together. And again, unsurprisingly, you can see that the sea ice thickness going through 2016 has almost disappeared. We also know glaciers are retreating globally. So this is a graph showing you the length of the glacier relative to the year. And many of the largest glaciers on the planet have substantially collapsed in the last 50 years or so. This is a video showing a time lapse of the Mendenhall Glacier. If you've never looked at the Google Earth Engine time lapse tool, it's a fascinating way to visualize changes on the Earth's surface. Here's the edge or the front of the glacier, and you can see over time the Mendenhall Glacier in Alaska has been slowly retreating back towards a sort of shallower position along this riverbed. And those changes start to accelerate as we move forward in time. Oops, sorry, my video is not perfect. So another thing that we can look at to understand what's happening on the planet is the amount of heat being stored in our oceans. And so this graph is showing us the total amount of ocean heat content at different depths, and then summed over the entire depth of the ocean. And so again, we see a clear picture of ocean warming. And these little spikes here are actually volcanic eruptions. So you can actually see the ocean cooling off in response to volcanic forcing, and I'll explain that in just a bit, very clearly punctuating these warming trends. And then finally, we know, and I'm sure you've heard in the media, that global average sea level is increasing over time. Sea level has risen by about 8 inches since 1880, and it's projected to accelerate dramatically as the Greenland ice shelves progressively collapse by between 1 and 4 feet by 2100. To put sea level risk at, I guess, in context, the elevation of Galveston Island is about 6 feet above sea level, and by the middle of the 21st century, we're expecting between 4 to 6 feet of sea level rise along the Texas Gulf Coast, which would inundate much of the energy infrastructure in Galveston. So key question 1, how do we know what's happening to the Earth? The answer to that is that we have multiple independent measurements showing that the atmosphere, land surfaces, and the oceans are all warming. This information comes to us from different types of measurements, whether it's satellite, in situ, weather station, they all confirm the same trend. A second key question, which I receive a lot in my job, is how does the current rate of warming compare to periods in the past? And is the warming and carbon dioxide rise unprecedented in the geologic record? Often I'll hear people make comments about how, oh, this has happened before and CO2 rise is natural. And so how do we answer this particular criticism? And we can answer it very clearly by looking into data from the planet's past. So our friend, the woolly mammoth here, who existed during Earth's last glacial maximum, gives us evidence that, for example, Earth was glaciated about 20,000 years ago. And we have direct evidence from multiple different records that confirm this. So the second tool I mentioned is PALEOCLIMATE data. Paleo meaning old climate data. So high resolution climate proxy records that span the last several thousand years can extend our information from the instrumental record. These are things like tree ring data, ice cores, cave deposits, coral reefs. And when we look at these different archives, we can measure things like changes in greenhouse gas concentrations, for example. And one of the really wonderful things about using ice core data is that as an ice core solidifies, whether in Antarctica or Greenland or even in the high Andes, the actual bubbles of air are directly trapped in the ice layer. So we can measure directly the carbon dioxide and methane concentrations in the ice cores for those horizons, and we can date them. So essentially this graph here is showing you the directly measured concentrations of greenhouse gases in parts per billion over the last 2,000 years. And you can see there's been very little variation over the last 2,000 years for carbon dioxide and methane. And predictably, as the Industrial Revolution hits, these values skyrocket in ice core records. Accompanying these direct measurements of changes in greenhouse gases, we have reconstructions from tree ring data that show us our famous hockey stick curve, which essentially states that the temperatures in the last 3 decades have been higher than any other time in the last millennium. And I'll ask you to take a look at this graph again and then this graph, and you'll see that they have very similar shapes, right? We have very little variation in temperature and in concentrations of greenhouse gases over the last millennium, followed by a very accelerated rise following the Industrial Revolution. So ice cores and tree rings show us fast warming accompanying the increase in anthropogenic CO2. I have some fans in my fan club who would say, oh, the past 1,000 years doesn't give us enough context in Earth's history. And, when I say that CO2 varies naturally, this isn't going far back enough. So we can go back much further. That's fine. We actually have ice core reconstructions stretching back about 1 million years at this point, which is incredible that we can make these measurements going back so far in time. And if we reconstruct once again the CO2 and temperature anomalies from ice cores, this is the picture we get. So these are temperature anomalies here, and carbon dioxide in red, and thousands of years before present. So here we are today, and this is 400,000 years ago. And we actually see our ice ages and interglacial cycles. So here's the last glacial here. And what we see, if we compare this to greenhouse gas concentrations today, compared to these ice core reconstructions, here we are in 2016 at about 401 parts per million. At 2017, we were at 410, and as I'm sure you've all heard, we've broken 412 parts per million in the atmosphere. So the upshot here is that there is absolutely no time in the last million years where Earth's greenhouse gas concentrations have been this high. There is no geologic precedent for greenhouse gas concentrations rising to these levels without human interaction with the atmosphere. So this common misconception is quite dangerous, that climate has always changed naturally and it always will. That is true. However, if we look at the history of our species, where have we been, climatically speaking, in hominin evolution in terms of the climate record? So if we look at some of our earliest ancestors, hominins started to evolve sort of in this key period around 2 to 3 million years ago, up until the evolution of Homo sapiens much more recently. But we started to have, standing hominin relatives starting about 2 to 3 million years ago. So this is when our species really evolved. And paleoclimate, I always like to quote Shakespeare's The Tempest here. What's past is prologue. And we can use this paleoclimate information to contextualize the types of climates which support human life. We can extend our reconstructions of how Earth's temperature has evolved many millions of years into the past. For example, in this period of Earth's past, about 50 to 500 million years ago, we know that dinosaurs roamed the Earth, and unsurprisingly, temperatures were quite a bit hotter during that time. But over the last 5 million years or so, Earth has been cooling down. Here are ice age cycles. This is zoomed in now, and this last part of the graph is zoomed in on the last 10,000 years. So Homo sapiens are sort of evolving in this time period in Earth's past, where Earth has gotten quite a bit colder compared to our hotter periods millions of years into the past. And just to put this in context, here's the temperature change we're expecting if we substantially reduce emissions over the next 50 years. Here's the change in temperature that we expect with a business as usual carbon emissions through the roof scenario, aka we don't do anything about climate change. So just eyeballing this, with a substantial reduction of emissions, we are still hitting temperatures where hominins have not evolved at all. We are not evolved to cope with these temperatures. And in a business as usual scenario, we're talking about, and forgive me for the joke, the types of temperatures that supported massive cold-blooded reptiles on Earth. So the bottom line here, and I say this somewhat in jest, but I'm perfectly serious, is that yes, climate has undergone major changes naturally in the past, but humans are not evolved to cope with the temperatures we're heading towards. At about 2 or 3 degrees of increased temperatures, most of the tropics would start to become uninhabitable, which will lead to substantial climate migration and refugee crises. So key question 2, how does the current rate of warming compare to periods in the past? Is the warming and CO2 rise unprecedented in the geologic record? The answer to this is that ice cores, tree rings, deep sea sediments from all over the globe show that the rate and magnitude of temperature and carbon dioxide increase is unprecedented in the geologic record. So we can attribute the changes by looking into the past to human activities very clearly. Finally, let's take a look at the third tool we use in climate science, which are climate models. And you'll often hear climate models referred to as general circulation models, which provide a physical or a physics-based basis for predicting Earth's climate under continued greenhouse forcing scenarios. And to build a climate model, essentially we break up the atmosphere and ocean into lots of smaller grid cells, and we add all the physical processes that control the motion and heat transfer in the atmosphere and the ocean. And we run these climate models forward in time, about 5 minutes at a time. So they're incredibly computationally expensive, as you can imagine. When we run our climate models, and this video I'm about to show you is actually an average of about 20 climate models that different groups around the world run, we see a future with much, much higher temperatures on Earth. So this is the temperature change in Fahrenheit that we expect going through the 21st century with a business as usual high carbon emission scenario. So again, these are anomalies compared to the 20th century. So these are all changes from the base period. You'll see this Arctic amplification, which shows much higher temperatures at the poles. The temperature anomalies, in orange here are on the order of 10 to 12 degrees Fahrenheit. So we've now cycled back to the early part of the 21st century. But keep your eye on the United States here as we enter the end of the 21st century. The magnitude of changes we're expecting sort of in the northern sectors of North America are hitting 20 degrees Fahrenheit from where they are today. So in a nutshell, what climate models tell us about our future is that given different amounts of CO2 emissions, which are shown here by these different colors, we can expect temperature anomalies that are hitting something between 3 to 5 degrees Celsius on average, global average temperature. So climate models tell us that without substantial mitigation, as shown in this navy blue curve, temperatures are going to rise to levels, again, which we have not seen on the planet for millions of years. Key question 3, which I think is the most crucial if you take away nothing else from my talk today. I really hope you can all focus in on this section of the talk because it's about attribution of climate change to human activities. So this question comes in the form usually of how could humans really be solely responsible for global warming? Aren't factors like solar radiation and volcanic aerosols more important? These are other things that can change the climate system. So in climate science, we partition these different, what we call forcings on the climate system into 2 different sections. So the amount of energy we receive from the sun does influence climate, and the amount of energy the sun puts out, and I'm not a solar physicist, so forgive me, does vary on just a little bit every 11 years or so, and there are also centennial scale changes in the amount of energy the sun releases to space. We also know that massive volcanic eruptions, if the aerosol particles that they emit enter the stratosphere, they actually reflect incoming solar radiation. And this is the basis for sulfate aerosol geoengineering. It's the same as what volcanic eruptions produce, a slight cooling over a few years, which eventually rains out of the atmosphere. But volcanic eruptions can substantially cool the planet if they are large enough. We also have human drivers of the climate system, such as the emissions of greenhouse gases from human activities, whether it's transportation, energy creation, agriculture, etc. So we have to keep these separate in our minds. So what are the relative contributions to the climate system and its changes from natural versus human climate drivers? We can actually quantify this quite easily. So we usually talk in climate science in units of watts per meter squared. So how much energy in watts is being retained or emitted by the atmosphere as a result of these changes in climate forcing. Volcanic eruptions can have a negative impact on forcing, so they cool the climate system by between minus 0.1 to, for very large eruptions, about minus 10 watts per meter squared. But because these particles don't remain in the atmosphere, they rain out, this cooling only lasts for about 2 to 5 years. Solar cycles give us about 0.2 maximum watts per meter squared changes over hundreds of years, okay? And then finally, human activities are generally categorized as forcing the atmosphere by about positive 3 watts per meter squared per year. And that number is unfortunately growing. So we're adding about 3 watts per meter squared to the atmosphere every year, retaining that additional energy in the climate system. So why do I raise climate models to you as a tool? These different climate forcings can be incorporated into climate model simulations. And we can actually partition, okay, let's say we run the climate model with volcanic forcing only, or we run it with solar forcing only. We can diagnose the various impacts of these individual components of the climate system. And when we do that, we get a graph that looks something like this. So here's the forcing, again, in watts per meter squared, so the energy retained or released by the atmosphere. Here in blue, we have our volcanic eruptions. Okay, so we have this short-term cooling anytime there's a sufficiently large volcanic eruption. Land use changes are here in green, very small. The sun's energy actually, like you'll see, varies at very small wiggly amounts, but it's not sufficient to drive the warming we observe now. And then finally, actually, aerosols from urban pollution have more recently been scattering incoming radiation. So they actually do cool the climate. Finally, the only forcing on our climate system that causes a positive response is greenhouse gas forcing. So this red line is what happens if we run the climate model just with greenhouse gases alone. And you'll see that it is the largest contribution to warming of any of these other different climate drivers. And when we talk about attribution, what we can say now with absolute confidence in the climate modeling community is that if we simulate the 20th century with natural climate drivers alone, what we get is this blue line. This is, again, the multi-model average for multiple climate modeling centers throughout the world. Temperature anomaly versus year, 20th century. We get, on average, this blue line. Black is the observed temperature record, again, global average temperature anomalies for the 20th century. So without adding any anthropogenic forcings, we get something that does not look like reality. It diverges from measurements starting in about 1960. When we add in human impacts to our climate models, we hit the target dead on. Not only does this tell us that our climate models are accurately simulating the 20th century, but it also tells us that without the human impacts, without those added greenhouse gas forcings, we cannot simulate the 20th century at all. So this means we can directly attribute human activities to the observed warming in the 20th century. This is not surprising. We are using the atmosphere as a dumping ground for excess CO2 to the tune of 7,000 times 1 million metric tons of carbon per year. As I mentioned earlier, the total extra radiation retained by the atmosphere due to human energy production alone is approximately 3 watts per meter squared per year. That doesn't sound like a large number. If we think about 3 watts, right, you've all installed a 60-watt light bulb, which is bigger than 3. So this is about the amount of light energy that you'd get from a sort of dark, cold Christmas tree, 3 watts. But what happens if we add up that number over the entire surface area of the planet? So 3 watts per meter squared times the entire surface area of the Earth in meters squared. If we were to sum that number, it's equal to the amount of energy released by 4 medium atomic explosions per second. Per second. So we are actually adding an incredible amount of additional energy to the global climate system every single year. To summarize, we have multiple independent lines of evidence that the atmosphere and ocean are warming. The rate and magnitude of temperature and CO2 change is unprecedented in the geologic record, and we have decades of evidence that this warming is a direct result of increasing greenhouse gas concentrations. In the latest Intergovernmental Panel on Climate Change report, the message was delivered loud and clear. Warming in the climate system is unequivocal. The human influence on the climate system is clear, and limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. The impacts of these changes are serious. What does climate change mean for us? Increased frequency and intensity of natural disasters is a big one. Droughts, hurricanes, flooding, heat waves, sea level rise. The timing of the seasons is changing. Intensity of the seasons is changing. We're expecting an additional 30 to 50 days over 100 degrees for Texas by the end of the century. Disease and respiratory problems are also directly linked to these impacts of climate change. And a common misconception that you hear, especially unfortunately from US citizens, is, well, climate change isn't affecting me. And at least here in Houston, right, we had one of the biggest hurricane seasons ever recorded in 2017. Here's Hurricane Harvey making landfall in the Gulf Coast. But that wasn't enough for our atmosphere in a climate change scenario. We then unfortunately had Irma develop just a few weeks later, which caused incredible disruptions to the state of Florida. And ironically, while all of this was going on, you have incredibly elevated forest fire seasons taking over much of the Pacific Northwest and Northern California. So climate change is absolutely already causing billions of dollars in damage in the United States. So this common misconception that, well, that doesn't happen where I live. I know I'm short on time, so I'll just quickly say this is a small schematic showing the types of changes that climate change is already having on different regions of the United States. And these problems will continue to worsen over time. This graph shows you the billion-dollar weather and climate disasters from 1980 to 2012. Climate change is expensive, and we can save money later by investing now, applying simple economic principles of discount rate. Unfortunately, we are in the lead here in Texas. We have had more than 50 climate disasters that have cost the state over $1 billion over the last several decades. In other regions of the country, we know that there have been severe droughts, which unfortunately have led to wildfires across the United States. These are also worsening. If we look at damages due to wildfires over time, average per decade, this is outdated. This number is actually much higher for the last decade, but the number of structures destroyed by wildfire per year is going up. This is a video showing climate model projected changes in soil moisture in the upper 30 centimeters of the soil column observed, and then moving into a climate projection for the United States. You can see pretty categorically that Most of the United States is expected to experience drying and more intense flooding, or excuse me, drought conditions by the end of the century. Flooding is not something I need to explain to all of you. Climate change will increase extreme precipitation events and cause sea level rise. In a 2100 extreme sea level rise scenario, multiple different organizations have created these short videos which show what Manhattan would look like were we to do nothing about our greenhouse gas emissions. Importantly, developing nations will be less capable of responding to these climate changes. So in Bangladesh, where people are concerned about how they will get their next meal, it's unlikely that they'll be able to spend billions of dollars building infrastructure to protect against sea level rise, such as what they've been able to do in the Netherlands, for example. Developing nations just simply don't have the same capacity to respond. Heat waves are also projected to increase. This is the number of days over 100 degrees in the 21st century. South and West Texas are getting hit hard. Unfortunately, those numbers are hitting 70 to 80. So we're talking about 2 to 3 months of additional days over 100 degrees in Texas. This is obviously going to have impacts on our economy. Many people work outside. How will they continue to do that safely? I already mentioned forest fires and drought. These are becoming more common in Texas, unfortunately. And then finally, I just want to make the note, I mentioned already that the number of billion-dollar events is increasing in many places around the United States. And this is a very simple prediction, again, based on physics. We know that as we warm up the atmosphere, a warmer atmosphere will store more water vapor via the Clausius-Clapeyron relation. And so for many years, climate scientists have been predicting as we warm up the climate system, the hydrological cycle will accelerate and the top 1% of precipitation events are likely to get worse. I showed this slide earlier. This is the lower Mississippi Delta. This is a figure showing the vast damage that was done, here in Texas during Hurricane Harvey. I don't know why this guy is smiling while he rafts through this intersection of Memorial and Shepherd, but just to hammer this home, these impacts are not in our future. They are happening now. So you understand the science and you understand the impacts. What can we do? I'm going to let my other panelists really spend most of their time on this, but I just wanted to make a quick plug for one of the things I teach my students about what we can do as individuals, not at the sort of federal level. You need to work to create consensus among your peers. So everybody needs clean water. Everybody needs clean air. We globally need livable temperatures, and we would be doing a lot better without the severity of natural disasters happening now. And I think the other thing that really brings people together is people appreciate conservation of wild lands and wild spaces, and these are things that you can use to create consensus amongst the people that you talk to and work with. The problem is solvable on 3 different levels: federal, city, state, and local, and then finally via individual actions. As one example, renewable energy is getting way cheaper. I recently switched my entire power bill to renewable energy, and we should ask for it. To curb global warming, we need to first do no harm. We should not be developing in floodplains. We need to invest in research to produce clean energy at scale and continue to lower the costs. We need job training. We need creation of additional clean power jobs. We need to incentivize fossil fuel companies to reduce their carbon emissions in a market way, and we need to clean up our existing messes. We need to clean up Superfund sites. These are the principles that I would apply in order to solve the problems related to climate change. I'll leave you with 2 thoughts, and thank you very much for your online attention. I know it's difficult to get through these long lectures. Human civilization is now truly a geologic force. We are affecting our own climate. We are engineering our own climate system, and we have the power to control our environment and our future. The scary thing about this is we are now heading into unknown territory, and we have quite a bit of work to do to ensure that we have a safe and productive future on this planet. And with that, I'll thank you very much for your attention. Please feel free to ask me any questions or get in touch with me using my email address. Thank you very much.